What we're going to look at now is a way to evaluate basic definite integrals to find the exact value. We've estimated them using Riemann sums and Simpson's rule and the trapezoidal rule, but now we have a way that we can exactly find what the value of a definite integral is. Remember when we started with an indefinite integral? We said that an indefinite integral was the integral of f of x dx, and when we took the antiderivative, we got capital F of x, and then we added plus c in order to represent every possible antiderivative. Then we went and wrote a definite integral as the integral from a to b of f of x dx. And we said that that equaled the total change in the function, whatever the function was. The answer was always a number. It was not a function. And we actually have a way that we can combine these to find an antiderivative of a function and then evaluate the function to find the total change. So we have an additional way to write the result of the integral from a to b of f of x dx. We say, let's take the antiderivative f of x, and then we will evaluate it from a to b. And so to evaluate it from a to b means when you find the antiderivative, plug in the upper limit b, subtract off what you get when you plug in the lower limit a. And the resulting number is the exact value for this limit. It's not for this integral. It's not an estimate. It is the exact value. Let's look at the fundamental theorem of calculus. Now, it says of calculus, but it also is of integral calculus, because that's what we're working with right now, are integrals. So let's see what that looks like, and then we'll do some examples. This example says we want to find the value of the definite integral from 1 to 4 of 1 over x cubed dx. So the first thing I want to do is take an antiderivative, but the basic antiderivative rules don't have a fraction in them unless it's 1 over x to the first power. So I have to rewrite this. So I have the integral from 1 to 4 of x to the negative 3 dx. And then from this, I can use the power rule. So you look back at your list of integrals in case you've forgotten what they were, and you use the power rule to evaluate it. X to the add 1 gives you negative 2 over negative 2. So I have found my capital F of x. I have found an antiderivative. And notice that the integral sign and the dx are gone now. So I use the form that says, okay, now what I do is I want to evaluate it from 1 to 4. This is f of x. I'm going to put in b, which is 4, subtract off, and then put in 1. But I think I want to simplify this a little bit first. I never like to work with negative exponents. So I'm going to rewrite this as 1 over my negative 2. I think I'll put the negative up there. 2, and then the x to the negative 2 becomes x squared in the bottom. And this will go from 1 to 4. So let's put the 4 in first. Negative 1 over 2 times 4 squared is 16. Minus, and now I'm going to put in the 1. Negative 1 over 2 times 1 squared is 1. So I have a negative 1 over 32 plus a half. Put all that together, probably using your calculator, and it's approximately 0.46875. We said we're going to find exact values, and I can get a common denominator and find the exact value. 1/2 would be 16/32. So this is exactly equal to 15/32. But in some cases, especially if it involves an application with money, you need a decimal value anyway. And as long as you use a lot of decimals, you're going to be fairly accurate. Let's look at another one. And this other one is going to look very similar to this. The only difference is my limit of integration is going to be from -1 to 4. So all I've done is I'm looking at a brand new integral, and this one goes from -1 to 4. Now the problem with that is this is 1 over x cubed. And in this function, f of x equals 1 over x cubed, x equal to 0 is not in the domain. I cannot have x equal to 0. And if you go from -1 to 4, right in the middle here is x equal to 0. So you can't cross over it. This is taken care of in the fundamental theorem. If you go back and read the very first line before you get to the integral sign parts, it says f of x must be continuous on the interval from a to b. So for this, f of x is not continuous on the interval from x equal to a to x equal to b. So we cannot use the fundamental theorem on this problem because of the -1 means it has to cross 0. So cannot use it here. The integral from 2 to 4 of 3 to the x minus e to the x over 2 dx. I'm still looking at basic functions, just 3 to the x and e to the x. Both of these are exponential. Let's take each piece individually. And I don't really have to do much in the way of changing. Integral from 2 to 4, 3 to the x minus, the only thing I'm going to do is write the 1/2 in front. I don't need u substitution on these. I can simply take the antiderivative of each piece. The antiderivative of 3 to the x is 1 over ln of 3. Remember, you have to go back and review those rules for integrals. And then times 3 to the x minus 1/2, constant multiplier, and the antiderivative of e to the x is e to the x. And then all of this together goes from 2 to 4. So you can split it up and do each piece from 2 to 4 and then combine them. I tend to do it like this and just put the 4 in both pieces and subtract and then put the 2 in. So I would have 3 to the 4th over ln of 3 minus e to the 4th over 2. So I'll go back to that form I started with. Minus, and now I'll put the 2 in place of x. So I have 3 squared over ln of 3 minus e squared over 2. So I have some things with the same denominator. I've got ln of 3 in 2 different places, so let's see if I can simplify that any. 3 to the 4th is 81. 3 squared is 9. 81 minus 9 is 72, so I can subtract those two with the same denominator. I cannot subtract e to the 4th and e squared. They're just stuck. They do have the same denominator, so I could combine them that way. For now, let's just leave this as minus e to the 4th over 2, and here minus makes that plus e squared over 2. You could put these together some way, maybe factor out the 1/2. You'd have to watch about changing sign. So it's possible that you could do that. Sometimes you'll see answers left in terms of e, and in that case you may actually see, let me think what this might be. I'm going to write the e squared first because it's plus. Factor out the 1/2. That will leave me with e squared minus e to the 4th. That's a possible way you could see an answer written. or you could put it all in the calculator and come up with an estimate, which is about 41.9. But remember, what we're looking at here is the exact way to find the way to find the exact value of the integral. But typically, with a lot of these, we do want to get a decimal value.